Well, first of all, could I thank the distinguished speakers who have spoken so kindly of me in the introduction to this. And could I also say what a great pleasure it is to have this opportunity to come to Malaysia, and the great honour that you do me by providing this magnificent hall for the talk and for your time in attending it. I would like to talk to you today about energy, and I would like to give you some high-level views of some of the challenges that are facing the world. In doing so, I shall be using some examples which come from the UK, and I hope you will forgive me if I have used the UK as an example, but that is the area where I can most easily access the information and the data to illustrate my points. I should say that I am not today going to try and give you any guidelines on energy policy for the next 5 years. I would like to talk at a more strategic level about some of the challenges that face the world. The title of my talk is The Magic Roundabout, and the first question is, what does the Magic Roundabout mean? Well, there are two possible explanations. In a town called Swindon in the UK, there is an extremely complex traffic control system consisting of multiple traffic islands with multiple paths. For those who know the area, it is possible to navigate rapidly through this complex system and achieve the direction that they wish. However, for those that are unfamiliar, it is equally possible to spend several minutes going round in circles to very little purpose. And that seemed to me to be a useful illustration of some of the developments and attempts at developments that have happened in energy. But I must say to you that although that is a good example, it's not the real purpose. The real inspiration for the title comes from a children's television program that was very popular in Europe about 30 years ago called The Magic Roundabout. And the reason I chose this is that although this was a program that held the attention, that fascinated the watchers, no one was ever quite sure what it was about. Nobody quite understood the real drivers. And that seemed to me to be a very good analogy to the current situation for energy. But there is also another aspect, because two of the characters, the first, the very hairy dog that you see at the front of the picture, was fueled solely by sugar, a well-known biofuel. And on the extreme right of the picture, the very small figure with the red head was totally mechanically powered. Instead of legs, he had springs at the bottom and would move around by the application of kinetic and potential energy. And that seemed to me to be a much better analogy to what we were talking about. But having explained the title, let me start by talking about energy. I would like to start with this image, which for me is very important. If you were a being from outside the Earth, a space traveller, and you were tempted to come towards the Earth, perhaps because you detected some radio emissions or some other instances, you would be coming to explore strange events. Why were there radio emissions? But as you approached the Earth, the first thing that you would see as it became larger would be an image like this. And the significance of this image is that you would immediately recognize that the Earth was populated by intelligent beings. Why? Because the Earth has got light. It is illuminated. You can see the pattern of dwellings and cities highlighted from far away in space. And as soon as you saw that, you would know that you were dealing with intelligence. Light is critical to modern human life. A French philosopher, actually a semiologist, but effectively a philosopher, wrote this phrase about the use of light in the United States. And he talks about the skylines illuminated in the middle of the night, the air conditioning systems cooling empty hotels, and the admiration that he had for this achievement of engineering. But the last sentence, for me, is the critical one. He describes it as the mindless luxury of a rich civilization, and yet of a civilization as scared to see the lights go out as was the hunter in the primitive night. And the presence of light is one of the major blessings that we have from our use of energy. And it is just one of the benefits that we gain from our easy access to energy. But that access has come at a price. I was in Hong Kong a few days ago, and Hong Kong is a territory that makes full use of available energy. At night, the skyline is totally illuminated by light, and consequently, I deduce that the people of Hong Kong must be extremely frightened of the dark because they work so hard to avoid it. To do that, of course, these days we use the technology that has been provided by modern power stations. And this image of the cooling towers in a power station, which shows the plume of water vapor from the cooling, perhaps serves also as an analogy of the other consequences of our current systems of using power. And that is that it involves the emission of carbon to the atmosphere in the form of carbon dioxide. And this graph shows for the UK the increase in the emissions of carbon from fossil sources over the last 250 years. And what you can see there is the rapid rise that was associated with the industrialization of the UK. And by looking at the different colours, which have come out on the screen, the big white block is coal, and then you can see in the later years the increasing use of oil and more recently natural gas. All of these contribute to the emission of carbon to the atmosphere. And if we look at the equivalent figures for the world, we can see that there is a similar pattern, albeit starting a little later than in the UK. The current figures for emissions of carbon from fossil sources to the atmosphere are approximately 7 billion tonnes of carbon each year. And that is equivalent to 25 billion tonnes of the carbon dioxide gas, which is the form in which it is emitted. That has had a significant impact on the climate and the environment. This is a demonstration of the concentration of carbon dioxide gas in the Earth's atmosphere. And this graph is over a period of 1,000 years. How do we know? Well, we can monitor the presence of carbon dioxide by looking at air trapped in the polar, the Antarctic and the Arctic ice, going back for a period of approximately 1,500 years, and more recently we've been able to measure it directly. And what you will see is that concentration has gone up from approximately 280 parts per million up to approaching 400 parts per million. The consequence of that, so the climate scientists tell us, is that we are seeing a gradual increase in the average temperature of the Earth because the carbon dioxide, even at the very small concentrations in which it is present, acts as a means of trapping the heat energy we receive from the sun. And the reason is that the higher frequency energy that arrives from the sun can pass through the carbon dioxide, but when it is absorbed at the Earth's surface and re-released at a lower source temperature, the different wavelength of light is actually trapped by the carbon dioxide in the atmosphere, so there is a limitation on the amount of heat that can be reflected. And this graph shows the estimates of average changes in global temperature for approximately 150 years, and we can see that there are signs that that is increasing quite dramatically. Now, although the increases are dramatic, they are small in absolute terms, fractions of a degree. But we are starting to see some impacts on the world around us. This is a photograph of the snow cap on the top of Mount Kilimanjaro in Africa, photographed approximately 15 years ago. And this is the same shot photographed 8 years ago, and if you were to look at it today, you would see exactly the same tendency. The normal cover of snow on the surface has disappeared, and it's believed that that is because we've seen a warming of the atmosphere. One second example is of a glacier in Peru in South America. And here is a photograph of that glacier in 1978, and you can see that there is ice which flows down from the mountain and fills the valley in the foreground of the shot. In 2002, that glacier had disappeared, and instead the valley was filled by a lake. Again, it is believed that this was due to a consequence of the increase in temperature. So, what do we believe the potential increase in temperature might cause? Well, about 18 months ago, a study was done in the UK of the potential economic implications of climate change if it happens. And this was performed by Sir Nicholas Stern, who published a very detailed report. And as part of that, he analysed all the available climate science evidence, and he said we can project what the impact will be for different levels of temperature change. And I must emphasise, these are the best estimates of the climate scientists. They may or may not be right. But at an increase of less than 1 degree, we start to see the disappearance of glaciers in mountains. As the temperature increases by 1 degree or more, we see a rising intensity of storms, droughts, and similar climatic events. At about 1.5 degrees, we start to see a reduction in the yield of food crops produced by agriculture. At about 2 degrees, there is a projected significant decrease in the availability of fresh water in the populated areas of the Earth. And increasingly, at that temperature, there is the potential that species will start to disappear from the Earth's biosystem. As we approach 3 degrees increase, there is a real risk of abrupt and large-scale shifts in the Earth's climate system. And over 4 degrees, there is the potential for significant rises in sea levels due to the melting of the polar ice caps, which would threaten a number of the major cities of the world, many of which were developed as ports originally. So, just in summary, the evidence that we have is that CO2 levels today, which are currently at 386 parts per million, are increasing as the result of our burning fuels by about 2 parts per million every year. The climate scientists say that if we wish to restrict temperature rise to 2 degrees, we should not allow the level in the atmosphere to exceed 450 parts per million. And at the present rate of development, it is likely that we will reach this point in the year 2035, so approximately 25 years from now. If we wished to delay arriving at that point by just 15 years, then the developed Western world alone would need to at least halve its emissions of fossil carbon starting today. That is an enormous challenge. This is the basis on which a number of governments have taken the decision that they need to take some action on climate change, and that energy and the use of energy is the major feature in that. I'm not going to try and persuade you that these data are correct, but simply to tell you that governments who set policy have decided that they should base policy on this data. Now, if we are going to cease using fossil carbon, there are some consequences. We must remember that 150 to 200 years ago, our use of fossil carbon was almost zero. And we can see what life was like then. On the left is a photograph from 130 years ago in the UK, showing the major means of transport for both people and goods, using animals to draw carts. And on the right, we see the major means of industrial food production, which was wind power to grind wheat to produce flour. This is a photograph from the same era of a mine where people were digging metal ore from the ground. And what is remarkable about this photograph is that everything in it is powered by animals or people. There is absolutely no use of any external form of power or energy. That was the norm in those days. However, we should not think that people had not developed means of using energy and of augmenting their own efforts. This is a photograph of a watermill developed in Egypt more than 2,000 years ago, and this watermill was used to help in food production using the energy of a flowing stream of water. We have, for many hundreds of years, made use of the power of the sun to dry food and for other purposes of heating and production. We have, of course, always used bioenergy. We've used bioenergy for food, and we've used it for fuel, particularly when we've been looking at cooking. We've used wind energy for transport. This is a photograph of a ship that was built more than 100 years ago and was developed specifically for international trade. Wind power we've already spoken of, and similarly the use of wood for cooking purposes. This is widespread in the world today. Consequently, we have a lot of experience of using non-fossil energies, but our use of them has not been efficient by modern technological standards. One of the disadvantages of many of these sources of energy is the energy density. And I have some figures here which shows the energy content of different fuels expressed in gigajoules per ton of the fuel. And if we look at the second line, for oil the figure is well in excess of 40. But if we compare that with wood, that is less than 1/4 the level. It is about 10. And if we look at the density of energy in natural sources, such as hydro energy or the wind, it is even lower at about 3.6. That is less than 1/10 the energy density. This is very significant if we wish to use these sources in the modern world. This photograph is a very crude attempt to show you what this means. The picture of the wood, if we assume the area of that photograph expresses the energy, the volume of the wood required for a fixed amount of energy, then the small picture of the oil in the lower right-hand corner shows you how much volume you need to store the same energy in the different form of oil, and on the left in coal. These, of course, are fossil energies. And one thing that's important to recognize is that fossil energies are convenient because they are very, very dense. I'd like to now move towards what the future may hold, because there are possibilities that we have that yet are not developed but offer promise. And the first example that I'd like to take is the use of coal in a more convenient form. In Australia, there is currently a large-scale experiment underway to take energy from coal, not classically by digging it out of the ground, but by causing an underground reaction which converts the hydrogen and carbon in the coal into a synthetic fuel gas. Effectively, steam and air are injected underground into the coal steams, where they react with the coal and they produce a gas that is a mixture of carbon monoxide and hydrogen. This gas can be turned into liquid fuels. It can be used directly as a substitute for natural gas. It's a cleaner way of using coal, but you may quite reasonably say, but you've still got the carbon contained within it, which is correct. However, once the coal is in the form of gas, it is technologically possible, even though the technologies are not yet fully developed, to capture the carbon in that gas and potentially return it underground and leave it there and extract all the energy simply in the form of hydrogen that is contained within the coal. This could be very significant. If I take the example of the UK, where there are extensive coal deposits, but they are very difficult to mine in a conventional way, and also they produce a coal which is of dubious quality because of the detailed trace contents, we can see that there are a number of areas where gasification is technically possible, and if we could realise that, it would represent an energy source that would meet all of the national energy needs for more than 400 years, simply based on extracting the energy from the coal underground in the form of hydrogen. More importantly, these areas where the coal is found are in areas where there has not traditionally been mining, and therefore they represent potentially an economic development for those particular areas. How do we store the carbon dioxide? Well, currently there is an experiment being conducted in the sea just off the UK, in the North Sea, in an oil field which is called Sleipner. And for the last several years, we have been storing gaseous carbon dioxide in sand deposits within that field at the rate of 1 million tonnes per year over more than 10 years. The purpose of this is to confirm that carbon dioxide as a gas can be stored continuously and safely. Now, you don't need to use sand. You can store carbon dioxide in different rocks, which are porous. But the particular sand that is being used is a sand of very fine grain, which when it is packed together leaves a large number of small voids or spaces within it. And the lower part of the picture here shows some scanning electron microscope images of what the sand looks like at a high magnification. Over the period of this experiment, there have been extensive geological surveys done to see what happens to the gas when you inject it into these sand formations. And if you look in the lower left-hand corner of this slide, it shows a perspective view in 3 dimensions of how the carbon dioxide gas is distributed in the various layers of sand deep underground. At the top right, there are 2 images taken by geological survey imaging, which equally show the extent of the carbon dioxide gas in the field. Now, these tests have been done to find out if the gas stays in one place or whether it moves away. And what we can see from the images that we have is that when you put it into the ground, it does appear to stay there. and therefore the potential of using this as a means of long-term storage of carbon is quite high. It's so high that there are a number of proposals in the UK to actually build power stations which incorporate this technology. This is a diagram of one particular proposal, and in the top right you can see that the plan is to take natural gas from the oil fields, to pass it through the yellow pipeline to a processing station where the gas is converted to hydrogen and carbon dioxide, and the carbon dioxide is then separated and it is pumped back out to a disused oil field, one that is almost depleted, and injected into that oil field. Based on the Sleipner data, we believe that this gas will then stay there. It has another advantage, which is that the injection of the carbon dioxide forces more natural gas and oil out of that well than can be obtained by other methods. So it increases the production of energy. The hydrogen itself is used either to generate electricity or to be used as an energy vector, an energy source that could be used perhaps in transport or for other purposes. The intent in the UK is that a power station similar to this, perhaps slightly different but similar to this, will be constructed in a few years' time to act as a demonstrator, with the intent that it will be a legal requirement that all new power stations have this technology, maybe starting 20 years from now. I'd now like to turn to another example of the use of fossil fuels, which is fuel cells. For those of you that are not familiar with fuel cells, they are electrochemical devices, very similar to a battery. The only difference is that a battery contains all its energy in its electrodes, whereas a fuel cell, the energy is supplied externally, so it will continue to operate for as long as you supply fuel. And there are two different types, which I've tried to show here, but I guess you might find that difficult to see, so I'll briefly describe it. On the right is a technology called proton exchange membrane fuel cells. Remember, this is like a battery, so there is an electrode, an electrolyte and a second electrode, the cathode and anode either side. In the proton exchange fuel cell, the electrolyte conducts protons, hydrogen ions. And I emphasize the word conduct. These do not diffuse through some kind of porous medium. This is a solid material, and it is an exchange through the structure of the electrolyte. On the left is a second type of fuel cell called a solid oxide fuel cell. The principle is very much the same, but in this case the electrolyte is actually a ceramic, and it conducts oxygen ions. To do this, it has to operate at very high temperatures, several hundred degrees Celsius, but because it conducts oxygen and not hydrogen, it means that the fuel cell can use a variety of different fuels, in contrast to the proton exchange cell, which must use hydrogen. Now, the structure of these materials is quite complex. There are porous electrodes either side of a solid electrolyte, and these are just a few microns in thickness, a few thousandths